So I think most students are here, so I can get started. So welcome to the second talk of our CRP seminar. So I'm the organizer, so I will introduce myself. So my name is Qing. I'm an assistant professor at the ECE department. So my research topic is mostly on non-convex optimization, machine learning, and learning low dimensional models from data. And recently, I'm very interested in deep representation learning, and this talk will broadly about understanding what deep learning and learning, what kind of representations deep learning and learning, where we will explain this through this called neural collapse phenomenon. So we'll study what is neural collapse and why neural collapse happens through optimization perspective. And finally, we'll discuss about the implications of such a result. So we can get started. So this is a major reference for this talk that we have published in the last 2 years. So before I talk about detail about what is neural collapse, I want to give an overview of what has done so far in deep learning and what are state-of-the-art theory for deep learning. So we know that in the past decades, we have witnessed tremendous success of deep learning in computer vision, natural language processing, gameplay, and protein modeling, healthcare, etc. Where this really kicks off around 2012, where the AlexNet have given us a significant boost in ImageNet classification challenges. And afterwards, the deep network has really revolutionized a lot of things that we're doing in engineering and science, like natural language processing and even autonomous driving, etc. That nowadays we were mentioning machine learning. What we're really mentioning is the state of art is really deep learning methods. And a vanilla deep network can be viewed as follows, where say we have some input data X, and the deep network is basically a hierarchical representation of our data, where we pass our input X through some weight matrices, followed by some nonlinear activations such as ReLU, max pooling, etc., and then followed by some linear operators, and repeat this process until the final layer. So the deep network is basically a nonlinear hierarchical representation of our data. And so the success of the deep learning can contribute to a lot of things. So one major thing is that so if you can view that a deep network is basically a feature extractor, that you have like input data X and output is a feature representation of our input data. And one of the key aspects that the success of deep learning is that nowadays the representations of features are learned rather than handcrafted from the data. On the other hand, so nowadays we have more data to train the deep network to learn the features. And recently there's a lot of network architecture design advances that better captures invariance or better approximation of our data. And the nonlinearities in our representations, such as max pooling or ReLU, that helps to capture the nonlinear structures inside of data. So there's a lot of advances in the negative actor design that really helps to boost the performance of deep learning. And the other aspect is in terms of optimization. So there's someone saying that the Zoom slide's not advancing. Sorry for this. waiting response.
I think you direct message somewhere.
Oh, sorry. Okay. Yes, this is better. So another advance is in terms of optimization, right? So we have better initialization, better optimization techniques, and have more computing resources that really helps us to train the deep networks to better solutions. However, it should be mentioned that the theoretical understandings of why deep learning works still remains shallow. There's a lot of mysteries in deep learning that not well understood reason still. So there's another chat. Let me see. Okay, it works. So one aspect is that there's a lot of hyperparameters for deep network to tune, like feature dimensions, the depths and widths of deep networks, and the use of activation functions that we don't have like a systematic approach to tune those hyperparameters. So another is in terms of optimization, right? So what kind of loss functions that we should choose, and what kind of optimization or normalization approach we should use during optimization, that people nowadays still based on heuristic and trial and error. And there's many other properties, important properties that are like completely open. So one is the generalization. So why like over-parameterized network generalize, and why deep networks like vulnerable to adversarial attack. So these are important questions that has not been, still haven't been well understood in the literature yet. So in terms of the advances of deep learning theory, so most of the recent works focus on the training aspects of deep networks. And they all based on various kind of simplifications. So one direction, like people when they're starting to study deep networks in 2016, they try to go linear. They like remove all the nonlinearities in the deep networks. They remove the ReLU, the max pooling layers. They just assume that the linear, deep linear networks, and they show that the deep networks can have deep linear networks can have some good optimization landscape properties, such as strict saddle properties. But I would say is that the power of deep network is really depends on the linearity or the nonlinear activation functions across layers. So if you remove the like nonlinear activations, then lose the power of nonlinear representations over data. So this is an assumption is kind of very far from why the deep network really works. So another direction people go is they go shallow. So they study like a very shallow deep network. Say they study a 2-layer or 1 hidden layer neural network. But I would say is that the shallow network, I mean, the power of deep network, another aspect is that really the depth plays a very important role in the success of deep learning. So the shallow network is still very far from what we have doing in practice. So quite recently, there's a line of work that people try to go wide. They study like ultra wide, highly over-parameterized deep network. And in this, for ultra wide deep network, this enters the so-called neural tangent kernel regime, where the deep network, the weight parameter of the network doesn't move too much. And it acts like a kernel regression problem. But another line of work trying to argue is that when you enter the neural tangent kernel regime, it's called lazy training. Actually, your weights doesn't change too much. And in practice, when you train deep networks, your weight will change significantly. So there's a substantial gap between theory and practice. So I would say is that most of the results the most results here hardly provide too very much insights or practical deep network training. So there's a substantial gap between theory and the practice yet. So in this talk, we try to bridge a little bit gap between theory and practice. So we still make a very strong assumption, but we try to understand what kind of representations deep network are really learning. So this is the topic of this talk. So in the past, people believe is that when we're looking at the representations of deep learning, so deep network is learning hierarchical representations. And people tend to believe is that in the shallow layers, the deep network are learning some basic elements or structures of our data, like what the dictionary learning are doing or wavelet spaces are doing. And when we're going further, people tend to believe is that the high-level features are capturing some semantic structures of our data. So the question is that is really the case in practice of modern over-parameterized deep networks. So in this talk, our answer is kind of negative. Actually, what we show is that the deep network in the last layers are learning, are just like fitting the labels rather than learning some like meaningful representations of our data. And we call this phenomenon neural collapse phenomenon. So for the rest of the talk, I will first introduce the concept of neural collapse. So what is neural collapse? And based on this, I will discuss about why neural collapse is happening and what is the potential implication of neural collapse. And finally, I will conclude this talk by some future directions and discussions based on our results. So next, I will introduce the basic concepts of neural collapse, which is a representation of deep networks that in the last layer. So to introduce this concept, I want to focus on this multi-class. So maybe I'll move this on a bit. I'll focus on this multi-class classification problems in the super setting. So the problem is that we are given a bunch of training data sets, and where X is our input images and Y is a label, the class label for the input data. And we consider multi-class classification problem. For example, our class can equal to 10 for MNIST or CIFAR data set, and it could be equal to 1,000 for ImageNet data set. And to do classification, the idea is that we have some input, say input data, X is the input image. And the learning, the super learning is that we learn a deep network from the input data to fit our output labels. So here, Y represents one hot label. So say if your input data, this image, lays in the first class, then the one hot label is basically your first entry equal to 1, which represents the first class, and all the other entries are equal to 0. So same thing happens for the second class. So one hot label is where the second entry is equal to 1, and all the other entries are equal to 0. So, and based on this, we are training a deep network to fit our input data to the labels. And the deep network we are considering is this just this vanilla, a fully connected network, where the WL is the final layer, it's a linear classifier, and everything before that we assume is that the feature or the representation of our input data X. So here, my understanding of deep network is that the depth of deep network is really like linearize your input data. Say, I mean, you have multi-class classification problem, and for each class, your data is lying on some nonlinear manifold. And the deep network, what the depth of the network is doing is like a linearization your data. And when you look at the final layers of a representation of your data, it's basically like can be linearly separable. So the depth is kind of linearize your data, and until your last layer, your representation is linearly separable. So you can use just a simple linear classifier, WL, to make the decision. And here, the neural collapse, when we are studying the neural collapse, we are focusing on the last layer representation, the H, and the last layer classifiers. And we want to study what kind of properties they have when you're training your network to convergence. So here we consider, I mean, for classification problems, usually we consider a cross-entropy. We usually use a cross-entropy loss. And to train the neural network, basically what we do is that we minimize this cross-entropy loss across all the data samples. And we plus a weight decay. So basically weight decay is an L2 regularization on your weight parameters of your network. And we minimize the network parameters through SGD or ADAM, use any training algorithm you like, and train the network parameters until your loss converges. And we're interested, what's the problem we're interested in is that what can when you train this loss function until convergence, what W and H looks like. So in recent work by Vardam and David Donohoe, they published in a paper in 2020. So they show this kind of phenomenon called neural collapse for this final layer classifiers and the features. So next I want to explain what is the neural collapse phenomenon is happening. So if you look at this animation, so this animation is basically illustrating this neural collapse phenomenon. So here, to understand what is animation doing, I want to like using this figure to illustrate what each point is representing. So here, this dot is representing the feature, the H, for each input data, say xi, where each different input data represents, so each different dot represents a different representation of different input data. And this blue column are representing the means for each specific class. And so this green and red column representing the column, the rows of the linear classifier W. So when you're looking at this animation, so what you can see is that this is a 3-class classification problem. And when you are training your network onto convergence, so what you can find is that for each class, the features for each individual class is collapsing to the means of that class. And on the other hand, so what you can observe is that the class means are actually formulating a structure which is called tight frame, equiangular tight frame structure, that the angles between all the means are equal, and they are forming and they are maximally separated to each other. So this is the key of the neural collapse. I'm not sure whether I explained this well. If you have any questions, you can ask now. And this is the key of this talk. So I want to pause here a little bit. Any questions for this animation? Or do I explain this neural class phenomenon clear enough?
Can you go back to the other slide?
This one?
Yeah, so when you say class 2 mean, is that the mean of the features? Or like, what is that the mean of?
So here, I mean, if you look at, so here we are focusing on so this is a vanilla deep network, right? So we are focusing on the last layer representation and the linear classifiers of the network. So for each different x, say xi here, we have a different representation hi.
Oh, so it's the mean of the representations for a given class?
Yes.
Okay.
So if you look at this figure, so each individual dot is representing a hi for different input data points.
Okay.
So this small dot is representing a feature for each individual sample. And we will look at the this blue column because we know the label for each individual class, right? So we can calculate the mean for the features for that class. So this blue column, so say here we have 3 classes. So this blue column is representing the mean of the features for that class 1. And this lighter blue column is representing the feature mean for class 2, and so on. And on the other hand, if you look at this red column, so remember we also have a linear classifier, right? So the red column is representing the row vector of this linear classifier. Is that clear?
What is the Simplex ETF vertex?
So the Simplex ETF, so if you will see that this, when the training converges, so you can see when training this to the convergence, the means are actually maximally separated to each other, and they have this equal angle structure, right?
Oh, okay.
So this is called like a Simplex ETF structure. Yeah, so basically you can say that when you're training your data to convergence, like you are learning like a maximum margin classifier for your features, right? So that's why on your training data, you can achieve like 100% accuracy, that your features are maximally separated to each other. Yes?
Like, what's your definition of convergence? Like, is it any local minimum or?
Oh, so your convergence means that your training loss decreases to like stable. Yeah. And I will mention is that the neural collapse is happening right after the terminal phase of training, is that when you train your training loss to 0 and you train longer, you will observe this kind of neural collapse phenomenon more severe.
Why do we not like this kind of structure?
I will discuss about this later, but I think the intuition is that, I mean, well, this is a representation or data, right? So if you look at this definition here, right? So this H is a representation of our input data. So what this phenomena is saying here is that for each class, you are collapsing all the structures of your, like the specific class. And the feature you learned for that class is one-dimensional. So this suggests that you are basically, for each class, you are learning a one-dimensional representation for that specific class. And that means that you basically lose all the information of that class. So you are just fitting the labels, one-hot labels there, right? Yeah, so I think that's, so maybe if your data are following the same distribution, say your test and training data follow the same distribution, and you're doing this kind of a memorization overfitting to the labels, maybe it's a good thing. But if you do some other stuff like transfer learning, right? If you're training your data on like this deep network on like on one distribution, and then we were doing this distribution shape test, it might not do good because you are memorizing or overfitting to your training data set. And when you are doing tests on other distributions, so then this might not be good. This is my understanding of this. Any other questions?
So training longer, do you mean that after we achieve the training accuracy to be 100%, but since the cross-entropy loss can always be decreasing arbitrarily close to zero, you're still.
Which means that your training like accuracy achieves like 100% or something.
Yeah, when you say keep training after converge.
Your training accuracy like achieves 100 accuracy.
Right, but like after you have 100% accuracy, since you're using like softmax, maybe your classification is 100% accurate, but when you use the divergence between the softmax and the one-hot vector, you can still get closer even if it doesn't change increase your accuracy.
Yeah, that's a good point. Yeah, I'm not sure about that, but yeah, this animation I think gives a good illustration of what neural collapse is. But actually, we can like describe it more precisely through some simple mathematical equations. So before that, I want to mention is that this neural collapse actually is happening on a variety of network architectures. Like people in this paper, people show that it's happening on ResNet, VGG network architectures, and they demonstrate this on MNIST and CIFAR and ImageNet data sets that this neural collapse phenomenon actually is prevalent across network architectures and data set. So to mathematically capture this neural collapse phenomenon, so here we assume that the training set is balanced. So say we have a 10-class classification problem where the training samples for each class is the same. And let's denote the last layer classifier WL using W. And we write H as a concatenation of all the samples, all the features for across the training data set. And based on this, what we can like mathematically describe neural collapse is that the neural collapse can be captured by 3 properties. The first is within class variability collapse on the features, right? So in this animation, so what we can see for the terminal phase of training is that for each class, the features are collapsing to their means, right? So mathematically, what we can describe is that for each class, the features HKI, where K is denoting a different class, and I is denoting the samples within that class, is collapsing to the mean of that class. So this is one aspect of neural collapse. So the second aspect, remember, is that the features are actually formulating, especially the feature means, are formulating an equiangular structure, right? It's called Simplex ETF. And actually, we can mathematically describe this equiangular tight frame structure, where we see is that the class means are forming a equiangular tight frame structure is that the transpose of the mean product with the multiply with a feature mean is equal to a constant multiply this quantity. And this describes the simplex ETF structure. And you can see that this is because this is like a matrix transpose together. So you can see that if you like multiply a rotational orthogonal matrix in the middle of H, it doesn't change the ETF structure. So which means that actually this is simplex ETF structure is rotational invariant. So if you just rotate your simplex ETF in the space, actually it doesn't change the structure of your solution. So the third property of this neural collapse phenomenon is the so-called self-diuretic collapse. Is that if you look again into this animation, so you can see the feature means aligning with the classifiers, the W, so the rows of W, right? So this is the third property where the last layer classifiers are perfectly matching with the class mean of the features. So all those three properties captures what the representations of the neural collapse, right? So we have within class variability collapse, convergence to simplex ETF, and this is self-diuretic collapse of the classifier and the features, and they together captures this neural collapse property of our representation and the classifier that we learned in the last layer of deep neural network. And based on this, you can see that basically once we learn the representations, then we can make a decision or classification just using a simple decision rules for this. So this is all about the basic concept of neural collapse. So next, I want to discuss why neural collapse is happening. So we'll introduce a method to analyze neural collapse and to explain why neural collapse is happening based on strong simplifications of the models. So any questions before this? So any other questions for the definition of neural collapse or this phenomenon? So if not, I will try to explain why this neural collapse phenomenon is happening in deep network training based on a strong assumption that we call this unconstrained feature model. First, I will study this problem based on this cross-entropy loss. So as I mentioned previously, and then actually this property or this analysis holds beyond this simple cross-entropy loss. And actually you can show is that for many training loss we design, like whether mean squared error loss, some people recently designed better loss such as focal loss or using label smoothing, etc., or different type of formulations like instead of putting penalty on your loss function, you can consider a constrained formulation or normalized formulation of your problem. And you can show that actually neural collapse is prevalent across loss function design and formulations for deep network training. And finally, I will discuss about the practical implications of this neural collapse. So given the neural collapse happens, what kind of implications or what kind of guidance we can guide for guiding practical network training and generalization. So this is the main topic of the rest of this talk. And the work, again, is based on a line of our recent work in the past 2 years. And the major contribution here we showed is that we show for different training laws, we can show a global landscape under this so-called unconstrained feature model. And the analysis can explain why neural collapse is happening in the last layer of a deep network training. So first, I want to discuss, present our results based on this cross-entropy loss, which is a commonly used loss function in deep network multi-class classification problem. And our key assumption for analyzing, so explaining why neural collapse is happening is based on this strong, but I think reasonable assumption of our representation. So here, our assumption here is that the features, the last layer features, we assume that it is a straight optimization variable. So if you look at this a fully connected network, obviously the feature is constrained by the network architecture here, right? But here because it's a nonlinear interactions across layers, if you want to analyze the training loss, the training dynamics, then this nonlinear activation, the interactions makes the analysis very extremely difficult. But on the other hand, so what we know is that modern network is usually highly over-parameterized, right? So modern network we are using has millions or billions network parameters and is highly over-parameterized. So they can almost approximate any points in the feature space. So based on this reasoning, we assume that the features is a free optimization variable. And based on this assumption, we consider analyzing the loss with respect to W and the feature H. And this results in a problem like this. But I want to argue is that this loss function here, although we make this a strong assumption that H is a free optimization variable, the loss function we consider here is still a highly non-convex loss functions. And I want to also mention is that there's a lot of recent lines try to study deep networks based on this unconstrained feature model as well. And there's some other works, they call this problem, this model, layer peeled model, where you can think of that the last layer is peeled from the rest of the layer. So it's kind of a, they call this vividly as a layer peeled model. So based on this model, there's a line of work trying to study problems, the global optimality conditions for this problem based on different formulations where they can show that the global solutions have this neural collapse property. But so global optimality condition for analyzing the loss doesn't guarantee efficient global convergence. Any questions?
Yeah, can I take a closer look to the previous loss function?
Yes.
So are you like training a model by solving this opportunity function?
In practice, when you train a deep network, you're not doing this, right? So you are like optimizing your network parameters, where the H actually is constrained by your network architecture, right? And you are more like minimizing the network parameters for H. So here we make a strong assumption that H is a free optimization variable, because the modern network is highly over-parameterized. It can almost approximate any points in the feature space. So that's why we make this assumption that H is a free optimization variable.
So this objective function is mainly for analysis purpose?
Yes, mainly for analysis purpose. Yes.
So why are you regularizing the values of W and H?
So when you assume that your H is a free optimization variable, right? So the only like regularization you can add is on the H. Mm-hmm. But in practice, I think there's a like difference. In practice, when you're adding this regularization, you're adding the regularization on the network parameters. You're not adding the regularization on H. This is right. Yeah. But later on, we showed a experiment. What we showed is that it's actually the difference, the performance difference between adding regularization on adding regularization on H and adding regularization on the network parameters. Actually, there's a very slight difference there. There's a minimal difference there. So you can, it's almost negligible. So yeah. So that's why this model assumptions we think is reasonable here. This loss function here. And also, I think there's a lot of different problem formulations people considered in the literature, where they add these constraints and this kind of non-negative, this inequality constraints on your features and the classifiers. But I think in practice, people commonly do is they just add this regularization, this penalty here, instead of adding this inequality constraints on your problem formulation. So that's why we consider this generalized version of this problem first. Yes.
Why do we include H in the optimization function. I mean, if you optimize W and B, it should be fixed once you know what is.
Yeah, so here we are optimizing W and H jointly. So it's a non-convex problem. So we will fix like a W and you only minimize with H. It could potentially be a convex problem here. Any other questions?
Oh, it's okay. It's because WH, it refers to like everything in the network before, but this W is the network, like the weights of the last layer.
So W is a linear classifier.
Right.
And
okay.
H is a feature.
Okay, so it's, yeah, you're like separating the network into the two parts.
Yeah,
It's just everything up there.
Yeah, so that's why it's also called linear period model.
Okay.
Yeah. So there's a tons of work trying to study based on this model. They consider different problem formulations, and this work showed that actually any global solution of under this loss function actually have this neural collapse property. But the thing is that showing global optimality of this loss actually doesn't guarantee efficient convergence to the global solutions. So in this work, we show a much stronger result here. So what we show is that we consider this non-convex loss function under this unconstrained feature model. We assume that the feature dimension, where the D is a dimension of H, is larger than the number of classes, where K is the number of classes. And what we show is that we show two results. So what we show is that any global solution to this non-convex loss function actually satisfies this neural collapse property as I mentioned in the previous section. So secondly, the global optimality condition actually does not guarantee, especially for non-convex functions, right? So global optimality doesn't guarantee that we can efficiently obtain the global solutions. So here, to guarantee, to explain why any training algorithm you pick converges to this neural collapse solution, we show a stronger result where we show is that the function we studied here actually has no local minimizers, and it's a strict saddle function that if you look at the Hessian always have a negative curvature for any non-global critical point. So maybe this is a little bit abstract. Here I want to explain this landscape analysis through visualization. So here, our loss function is obviously like a non-convex, right? So it's something like this. But the nice thing here is that every global solution, local solution, is corresponding to neural collapse solutions. So the difference between all the global solutions is that you remember neural collapse solution is like a rotational invariant, right? So if you rotate your equiangular tight frame, it's still like a equiangular, like simplex ETF. So here, basically all the global solutions are equivalent up to a rotational symmetry. So on the other hand, what we show here is that the optimization landscape is benign in the sense that if you have like a critical point that is not the global minimizer, actually the strict saddle point. So here what I mean strict saddle points is a visualization like this, where although your gradient is equal to 0, but your Hessian is like a non-degenerate, that you can always find a negative eigenvector direction where the eigenvalues of your Hessian that could be negative, such that you can follow the negative eigenvector direction to descend your function. So this is called a strict saddle point. So our analysis is basically saying is that the loss function we considered here is a strict saddle function, like what we visualized previously, which means that there's no superlocal mean matters, and all the other non-global saddle points are actually a strict, global critical points is a strict saddle points where you can utilize your Hessian information to escape such a saddle point and descend your function value until you find the global solutions efficiently. And this landscape analysis showing here is basically suggesting that when considering the optimization landscape only with respect to W and H, you can always design some efficient optimization algorithm to explore the function landscape to find the global solution efficiently. That's the implication of our K result. And next, I want to discuss of the result to related works. So one thing that you can observe here is that the problem formulation, once you assume this unconstrained feature model, and the problem formulation we consider here actually is pretty close to a matrix factorization problem. So if you look at this, you can look at this penalty here, and this penalty actually is pretty close to the nuclear norm of W multiply H, right? So you can show that the minimization of W and H is equal to the nuclear norm of this W multiply H. So this is pretty close to a low rank matrix factorization problem, actually. So actually the analysis we showed here for this global landscape analysis borrowed a lot of techniques that from analyzing the landscapes for low rank matrix factorization.
Which matrix do you assume to be low rank?
So this is here is a nuclear norm, right? So here, not essentially this W multiply H, but this is not essentially low rank, but it's just this is a nuclear norm. This is equal to the nuclear norm of this whole quantity, right? So we can borrow a lot of the tools for analyzing this matrix factorization to analyze this neural collapse problem. So let me just erase this.
So you said that all of the local solutions form like an equivalence classic global solutions?
Yes, because if you look at back to the
right, but like I guess my question was, if they do form like this class, can you like move from one solution to the other like analytically, or is that not really worth doing?
You can just, if you find one solution, right, so you can just do a rotation.
Okay.
And you like random rotation, you can rotate to other solution.
Okay.
So the first comment I want to make to related work is that the results actually closely related to low rank matrix factorization problems. Here, the difference here is that here we are studying as a classification problem, and low rank matrix factorization is usually casting the problem as a recovery problem. And for low rank matrix factorization, so the observation is like generated, like we assume a generative model, and the Y, the observation is generated from that specific model. And here, because we are considering a classification problem where the Y we have is a very special structure, is a one-hot labels, right? The concatenation of one-hot labels. So that's why the problem so have this kind of a neural collapse structure. And when we consider matrix factorization, often we assume some statistic properties of our sensing matrices. But here, all the analysis is deterministic. And the global solutions here is like a special case of you can view this as a special case of matrix factorization. And on the other hand, I want to compare our results to a lot of the recent work trying to study like the training dynamics of deep networks. So here, I think the perspective is a little bit different. So, so a lot of previous works where they try to study like 2-layer or deeper neural networks, they often study the network from the input to the output, right? So whether the NTK analysis or the learning dynamics or mean field analysis, they try to study the dynamics from building a network from the input to the output, and they try to study this the learning dynamic. Here, we make this unconstrained feature model where we try to study the representations from the output and to the input layers. So we kind of take a top-down approach, right? So the previous methods is trying to take a bottom-up approach. So I think the advantage here is that by taking this bottom-down approach, we can better understand what kind of representations deep network are learning in this neural collapse structure. But the drawback of our approach is that we lost the input and output data relationship, right? So if we want to study like a generalization or robustness of network, because we lose the input and output relationship, it makes the framework impossible. So this is a drawback of our analysis. But I will say is that our work explains what kind of features deep network are learning, and also this well connects to the empirical phenomena that really happenings in practical deep network training. So next, I want to show you some results. So first result we want to show is that the neural collapse actually is, as we show in the landscape analysis, right? So the landscape is independent of the training algorithm, right? So the first experiment we show is that the neural collapse is happening independent of the particular algorithm that we are training. So here, what we show for each individual figure, we are plotting here, the x-axis is denoting the training epochs, and the y-axis is denoting each metric measuring the neural collapse. So the NC1 to NC3 are measuring different aspects of neural collapse, right? So the first one is measuring the variability collapse. The second is measuring convergence to simplex ETF. And the third is measuring the convergence, the duality convergence. And the smaller of those metrics means that the better the collapse is happening. And you can see that across different algorithms that we're using, actually the neural collapse is always happening. Although the collapse degree is different, but you can see that for different algorithms, you always have this neural collapse phenomenon. So which means that neural collapse actually is kind of algorithm independent. But since different algorithms have different like implicit bias towards different solutions, so the generalization performance is still like different. So the second experiment that we did is that the neural collapse, so we make in this, our analysis, we made a strong assumption of this unconstrained feature model, right? Yes.
Sorry, can you go, why would the optimizer make a difference, like you said, than in the performance if your claim is, you know, this theme that all local minima are global?
But that's only with respect to W and H, right? So when you're looking at the H, it's actually essentially like over-parameterized neural network. You can have infinite many solutions.
Right, but
the
it's
different
really...
algorithm, if when you train the network on the network parameters, it can have implicit bias towards different like network parameters.
But isn't your
SGD can also get stuck in saddle points?
It's measured.
But for W and H, you won't like stuck at a set of points, right? So for W and H, in our work, we show that W and H have always converge global solutions. But for W, for like a specific H, we converges to because it's like represented by parameterized by a network. And the network is highly over-parameterized. It can have infinite many solutions. And when you're considering the specific algorithms, it can like have implicit bias towards different solutions. That's why the generalization performance could be different.
So I guess this is maybe where your assumption is a bit strong that H can be represented
by different, by many other network parameters, different network parameters. So there's another question. Isn't the property simply because of Frobenius norm of Dublin unitary invariant? No, I don't think so. So I think it's, I mean, the H here can be parameterized. I mean, it's by an over-parameterized network. And that's the reason that the generalization performance is different, because different algorithms can have different solutions for that specific H.
So you're saying that there could be spurious local minima?
Yeah, it could. I mean, if you consider the network parameters, obviously there could be spurious local minima. But when you consider W and H, there's no spurious local minima. Here's the difference.
Sure.
Yeah.
Is there one optimizer that you found generally works better?
That's a good question. So usually, I think Adam or this works pretty well, or the SGD, just the vanilla SGD. Yeah, the LBFGS is not working that well. So you can see from this generalization performance, the LBFGS is not working so well here.
Second order.
Yeah, it's like a quasi, like a 1.5 order algorithm. I think the time is limited. I'm running out of time. So here, so the second experiment we did is that we showed we try to validate the unconstrained Fisher model. So here, what we do is that we train our network on this CFAR data set. But here, what we assume is that we just, for each input training sample, we assume like assign a random label. And if you given the random label, what you observe here is that once you increase the depth of the width of the network, you will, like once your depth increases, a width of network increases, which means that your network become more and more over-parameterized. You have more and more severe neural collapse. So this suggests actually when your network is highly over-parameterized enough, then actually the output of is kind of just trying to fit in the random labels, right? So it's kind of independent of your input. So this suggests that actually for over-parameterized networks, this unconstrained feature model is a valid assumption for starting such a problem. And given the interest of time, so I want to skip some experiment. I want to mention some of the recent work we did. Is that nowadays when you look at self-super learning or other, people tends to do normalization of your features, right? So and your weight classifiers. So a recent study, what we do is that we study the same problem under unconstrained feature model, where we normalize our features and the weight and the classifiers, and we consider such a formulation. And we showed is that similar global landscape also holds, and this is a work by John and Peng here. And we also show that under this normalized features, we show that we can have some advantages in terms of training and generalization performance. And actually, this neural collapse phenomenon is happening just beyond this cross-entropy loss. Actually, we show that this property also holds for mean square error loss. And actually, we studied this loss function, many other loss functions like focal loss and label smoothing loss functions quite recently. Actually, we show that if you look at this figure, you can see that for different losses, when you're training your network onto convergence, the neural collapse is always happening here. It's a prevalent crosses across different losses. And so basically what we're suggesting, the neural collapse suggesting is that as long as you can, those metrics are converging to zero, actually those losses design toward the same goal. It's just to minimize the neural collapse metrics. So I don't think I have time to discuss the implication of neural collapse. So I think I will just, given the limitation of time, I will just conclude this talk. So in this talk, we studied this neural collapse phenomenon under the unconstrained feature models. And I think this study could have further potentials and shedding lights of generalization or other properties of deep representation learning. So one of the remaining questions that is of great importance here is that the neural collapse phenomenon, whether it's happening prevalent across data sets and network architectures, but what is this a blessing or a curse? So in other words, is this a good phenomenon? Is a bad phenomenon here? So my understanding is that when you're considering that your data, your training and the test data are following the same distribution, then overfitting or like a memorization, maybe it's a good thing that if your test and training data follow the same distribution, then neural collapse is a good phenomenon. But when you considering other challenging tasks like adversarial training, adversarial robustness, or transfer learning, collapsing your features to one dimension that you loses all the information of your data could be a curse or like a bad thing. So that's why one of the reasons why it's very challenging for deep networks to do unsupervised learning. So there's some recent work by, I think, if you attended the EMAS talk in March, you know that he's proposing a framework called maximum rate reduction framework, where he's proposing a loss function trying to preventing this neural collapse phenomenon. And the loss he proposed is to learn features for each class, they're learning the features as a union of subspaces, where each class, where you can learn the intrinsic dimensionality of that class by transforming your data through a neural network to a union of subspaces. So, and the future work is that how can we just to quantify, and work in a setting that we, so how can we principally to prevent this neural collapse, and how can we explore the benefit by preventing the collapse and learning features like lies on the union of subspaces. So I think this could be a very interesting question to be further explored in the future. And finally, I want to thank all the people also. Sorry, I think I missed John here. Yeah, I'm sorry about this. And thank you all. Any further questions?
Any way to justify the free optimization assumption of the last layer feature each of it, besides the fact that deep neural network with high-level parameters?
So you mean is there any theoretical justification of this?
Or is it even possible to assume the last feature layer is free of?
I think here we just for the ease of analysis, we make this a very strong assumption. And if you are talking about, your question is that whether there's a theoretical justification, this is a really good model for this. So my answer to this is that, I mean, here the model assumption is still quite simple and quite strong, right? So although, I mean, here it's mostly for analysis purpose. So, and one of the future direction is that how can we consider say a 2 or 3 layer network, and we can analyze this neural collapse phenomenon under a more realistic model. Yeah. And another thing I want to mention is that the connection, I mean, the validation is, I mean, we did some experiments to validate the unconstrained feature model, but in theory, I don't think this is a really like a great model for analyzing deep neural network. So because we lose the input and output relationship there. Any other questions? Oh, there's a question in the chat. What would the benefit of avoiding neural collapse? So I think the benefit, as I mentioned, is that a neural collapse is that basically you are like collapsing your feature representation for each class to one dimension, that you lose all the intrinsic structure of data. And because you're losing the structure of data, so you cannot do like unsupervised learning, right? Because the representation you learn is not representation, like it doesn't capture the structure of your the data enough. Another thing is that when you're doing like a transfer learning or like a and also robustness. So I think the neural collapse actually is a bad thing there. You will perform poorly for those tasks.
Well, if your final layer is a linear classifier, like how much structure can you actually use? Like you might be able to preserve a decent amount of structure using a different method, but like how much would actually be useful for the linear classifier? Because it still needs to be linearly separable.
Yeah, but I think the depth is playing a role to linearize your representation, right? To make your data more and more linearly separable. So I think a linear classifier is still good enough. Mm-hmm. Because when you have like enough depth of network, so each layer of the network actually is trying to linearize your data, make them more and more linearly separable.
Okay.
So if you have enough depth of your like a network architecture, so at the end of the layer, so the final representation is linearly separable enough. But the thing here is that whether you are taking the neural collapse or you are like mapping your data to a union of subspaces. Mm-hmm. Because mapping to neural collapse is that you're losing the dimension of your input data, but the union subspace you can like better preserve the intrinsic structure.
Okay, so you're saying because you're collapsing it to just individual points for each class, no matter how large like that final dimension is, like no matter how many dimensions your hyperplane is in your linear classifier, it's only going to be like a I don't know, like a two-dimensional like classification problem. But if you were to preserve features, you could preserve features like linearly separable features in a high dimensional space where you could encode like a decent amount of information.
Right.
Because the space is so large.
Right.
Okay.
Yeah, exactly.
Okay, that makes sense.
Yes.
We're also abstracting away like the idea of like an activation function, right, in this model, because
so there's no activation functions there, nonlinear activation function.
But the activation functions are implicit in the H, aren't they?
Yeah, right.
So like we couldn't have like I guess maybe you could have a binary classifier, but you couldn't have a binary classifier used with like the sigmoidal activation function. It'd have to be like the hyperplane classifier, right?
Sorry, can you?
Yeah, so like one way of doing binary classification is you do a sigmoidal activation function on
yeah.
Yeah, so I'm saying like it couldn't model that. It would have to model it as a hyperplane classifier.
Yeah, right. Yeah. Okay, so no questions. Reasoning. What's the intuitive reasoning behind the occurrence of neural collapse? So I think the intuitive reasoning is because we have one-hot labels, and basically the one-hot labels are like orthogonal to each other. Yeah. So and you are overfitting to those one-hot labels, and then you have this kind of 90-degree like a structure for your representation. But network is basically you have a bias term, and then the representation you are learning is like a larger than 90-degree. So you can have like a larger angle there. Yeah. So I think the intuition is basically the network is overfitting to your labels, one-hot labels. Okay, so I think this is the end of today's lecture. Thanks.